Okay, let's go ahead and work our first example here. I want to find the mass of this right circular cylinder here. I assume that its density function is f of xyz equals 1 plus xz, grams per cubic centimeter. Okay, so the mass will be in grams. All measurements here, length measurements, are in terms of centimeters then. Okay, the right circular cylinder is supposed to have an axis of symmetry being the positive z-axis here. It's bounded by the xy plane. It's also bounded on top by the plane z equals 3. So we've got z equals 0 and z equals 3 as boundaries here. Okay, the radius of the cylinder is 1. Okay, let's go ahead and write an expression for the mass of this cylinder. Okay, so it would be the density, right, times differential volume integrated over the entire cylinder, which we're calling the solid S. Okay, well, the first thing you would need to see is what? Well, this cylinder has an axis of symmetry being the z-axis, so it seems like using cylindrical coordinates might be a good thing to do, in which case I'm going to have change x into r cosine theta. So I'll write rz cosine theta. And then we'll have what? R dz dr d theta. Okay, this will be pretty much our typical order here. Where is z going from and to? It's always going from 0 to 3, right? And where's r going from and to? It's going from 0 out to 1. And what about theta? You're going all the way around, so it's going from 0 to 2 pi. Okay, so this is the integral we're looking at here. Do not forget that r in there. Okay, now you notice the limits of integration are what? Or they're all constant, right? There's no functions here for limits of integration. That's because we're using our cylindrical coordinates here on a cylinder, okay, that's positioned just right. Okay, let's go ahead and think about actually working this problem now. The innermost integral, we would be integrating from 0 to 3, r plus r squared, z cosine theta dz. Okay. Alrighty. Let's go to integrate with respect to z. That means I'm what? Treating r and theta like constants here. Okay, so this would be rz plus 1/2 r squared z squared cosine theta. And z is going from 0 to 3. Okay. Oh, by the way, you notice I could have actually broken this into two integrals and taken out the r and the r squared and cosine theta because they're acting like constants. You could do that if you want. I'm not going to bother here. Let's see, z is 3. Okay, so I get 3r. And then I get what? 9 halves r squared cosine theta. When I evaluate at 0, I get 0, so that's what the result we get for the innermost integral. And then we're going to integrate that with respect to r. And let's see, r is going from 0 to 1. So we're going to go 3r plus 9 halves r squared cosine theta. Okay. And then that's dr. Remember, I already had that r in there as a factor in the previous one. Okay, so we're doing well. Okay, 3 halves r squared plus, it looks like 3 halves r cubed cosine theta, because what theta is acting like a constant. We're keeping that fixed and integrating with respect to r. Okay, r is going from what? 0 to 1. Okay. Let's see, at 1 we would get 3 halves plus 3 halves cosine theta. And at 0, we would get 0. So we've got that for a difference here. Okay. Finally, we've got to integrate this for our mass here. 0 to 2 pi. 3 halves plus 3 halves cosine theta. d theta. If you guys are really quick about this, is this lazy or is this efficient? When I integrate the cosine, I'm going to get what? A sine, right? Going from 0 to 2 pi, you can see it's going to be 0 minus 0. So I really get 3 halves theta from 0 to 2 pi. So this is actually going to end up being what? 3 pi, I think. Okay? All right. So there's our first example there. Okay, for our second example, what I want to think about doing is not actually evaluating an integral, but setting it up properly. Okay, because as you know, sometimes that could be the real challenge. All right, suppose I'm talking about the triple integral over the solid S of some function of x, y, and z dv. Okay, now S is, let's describe S. S is the solid bounded by the interior of this. X squared plus y squared plus z squared equals 6. And above the paraboloid z equals x squared plus y squared. Well, first of all, if you give this a little thought here, you can see pretty quickly that we're talking about the interior of a sphere centered at the origin with radius square root of 6, right? And then this paraboloid opening upwards, right? Okay, let's go ahead and take a quick peek. I actually graphed this on GeoGebra, and this is the critter we're looking at here. This is the z-axis here. Let's go ahead and label that. Okay, and here's my sphere centered at the origin with radius square root of 6, and there is that paraboloid. So what I'm attempting to do is attempting to integrate over this figure here. Okay, this figure that's inside the sphere but lies above that paraboloid. So you see this kind of an acorn shape or something like that. Okay, I hope that's coming through here. Let me push it in a little closer. Do you guys see the sort of the acorn shape? That's our solid S, okay, that we're trying to integrate over. All right. Now, when you do this, you guys can see I'm using cylindrical coordinates, so that's obviously going to come into it here. Setting up the limits of integration is the real problem. What I want to do is imagine the following. First of all, if I'm going to integrate with respect to cylindrical coordinates, what I want to do is actually find the equation of the intersection of that paraboloid in that sphere. Okay? Just for a second here, can you see that the intersection of the two is actually be what? A curve that is a circle that's parallel to the xy plane. Okay, can you see that there? So that's actually a circle here. We actually need to find that circle there because in setting up our limits of integration, I'm going to imagine taking that circle as boundary and projecting that down into the xy plane, then integrating in the z direction properly. Okay, which would be the first thing, first direction I'm going to integrate. So let me ask you this question then. If I have these two and I'm going to intersect them in 3 space here, then we know we should get what? A circle that actually lies, we'll show you in a certain plane here, parallel to the xy plane. Okay, how would you go about solving that though? Well, if I've got x squared plus y squared plus z squared equals 6, but x squared plus y squared is z, then couldn't I just reduce this problem to a single variable problem and go z squared plus z equals 6? In other words, z squared plus z minus 6 is 0. Let's go ahead and solve this by factoring. That would be what? Z plus 3 times z minus 2 is equal to 0. Okay? And you can see there's only going to be one solution that's of interest to us. It's actually z equals 2, because you can tell here that this second solution, z equals negative 3, is extraneous. Obviously, these two surfaces do not intersect at any points with a negative z value here. Okay? This is actually just the plane in which that curve lies. I have not actually completely determined that curve yet. Okay? But you can see that it's going to lie in a plane which is what? Parallel to the xy plane, like I stated just a minute ago, right? The xy plane would have equation z equals 0. Okay, now this isn't all, the intersection of these two is not all points where z equals 2. Remember, we still have this stipulation here that z is x squared plus y squared. It has to lie what? Has to lie, for example, on this paraboloid. So we're actually going to put these two together. Okay, so it's the circle with radius 2 centered at what? 0, 0, 2. Okay, and if you look at that, wait a minute, that looks very believable, right? Okay, all right. Now I'm actually going to take this circle and I'm going to project it down into the xy plane. Okay, so this is the circle I'm really interested in. Okay, all right, because this is going to be my region R over which I'm going to integrate in the xy plane, thinking in terms though of what? Polar coordinates and really cylindrical coordinates as well, because we've got r, theta, and z involved. Okay, so far so good? All right. So let's come over here. Let's continue then. What would be my limits of integration here? Alrighty. Now I've got f of what? R cosine theta, because that's my x, right? My y is r sine theta. And then I've got what? Z. And then I'm going to have what? R dz dr d theta. Okay. And I didn't even say what this represents here. I guess I'll just call it my integral r. I guess I could have done that from the beginning. No particular interpretation on this. It's just an abstraction here. Okay. All right. Now wait. Where are the limit? Where's z going from and to? Okay. Z's going from where? At each point here, it's going from the paraboloid up to the sphere. Okay. So that means it's going from the paraboloid, z equals x squared plus y squared. Okay. But wait a minute. We've got to use what kind of coordinates? Oh yeah, we've got to use cylindrical coordinates. So that's polar in x and y. So I'm really going from z equals r squared, right? Because that's x squared plus y squared, up to what? Z equals 6 minus x squared plus y squared. And don't forget to take the positive square root, right? So all I really did was come back here and write both these in terms of what? Cylindrical coordinates, okay? So that's what? Z equals r squared. This would be what? Z equals the square root of 6 minus r squared, okay? I'm using the positive value again because you can see here that we're going to the positive value in z, okay? Now, if I project this region over which I'm integrating here down onto the xy plane, then I'm dealing with the interior of this circle, right, in the xy plane. Okay. We're not really using Cartesian coordinates, but they're going to help orient us here. So I'm looking at this, right? This was my circle, and I'm integrating over the interior of that thing. Okay? Because if I take all the points in my acorn and project them down into the xy plane, I get that thing. Okay? All the points in my acorn get projected down into the xy plane right there. Okay? Let's maybe do this here. Okay? Now, think in terms of polar coordinates now, because we're actually done with z, right? Technically cylindrical, but think in terms of polar now. Where's r always going from and to? R is always going from 0 out to, oh, wait, wouldn't that just be in polar coordinates? R equals the square root of 2? Yeah, x squared plus y squared is r squared. So this would be the equivalent edge of the circle, right? This is actually the whole disk, but that would be the boundary. R equals the square root of 2. So we would go to from 0 to the square root of 2. Now, where's theta going? Theta is always going all the way around. So it's going from 0 to 2 pi. So this would be the final answer there. Okay? Alrighty? Maybe you don't like that Z there. There. Box in your final answer usually, but there it is. Alrighty? All right, let's look at one more example here at least. Okay, let's work one more problem here. Find the volume of the ice cream cone. I've drawn a picture for you here. That's formed in the following way. It's inside the sphere, rho equals A. Yes, I'm using what? Spherical coordinates. Okay, I'm not going to solve it that way though. But it lies inside the sphere, rho equals A. And then it lies above the cone, phi equals alpha. Now you remember spherical coordinates, right? How do you measure phi? You measure phi from the positive z-axis, okay? So I've drawn a little picture here for us, and this is supposed to be, this means perpendicular right there. Okay, I've drawn a little picture so we've got an idea of what we're looking at here. It sort of looks like an ice cream cone, so that's what I called it here. I'm trying to find its volume, okay? I'm going to try to find the volume of this thing, all right? Now, one thing I might mention here, even though I haven't completely done that yet on this part, do you see these two are going to intersect in a circle of a certain radius, and then if I project that down into the xy plane, I will get a circular disc centered at the origin that I've called R for region here. I'm going to be integrating ultimately over that R here. Of course, we're using cylindrical coordinates, so we're going to integrate in the z direction first, and then we'll be integrating over R using polar coordinates. That's the essence of cylindrical coordinates here. Okay, now let me emphasize here that the A and the alpha are fixed, right? This is a fixed radius, and alpha is a fixed angle. So phi equals alpha. Alpha is some angle between 0 and pi. Okay, now on this region R, I'm going to imagine a certain point here. See here marked in black here, and I'll say that radius is R. Since everything here is symmetrical about the z-axis, we don't really have to worry about theta very much, do we? Okay, that's going to be really easy with respect to theta. So I didn't even pay attention to theta here. I just paid attention to this point as a certain distance from the origin in the xy plane. So I'm calling that little r there. I hope you can see that. Now, just above that point, I've got what, a point here on the cone. Okay, so it has the same coordinates, r and theta, or x and y if you wish, as the point here, but it's got a different z value. That z value is lies on the cone, and there's a z value above that with those same x and y, or respectively r and theta coordinates, that lies on the sphere, right? Okay, so these lie right above each other. So I called this the lower z and the upper z corresponding to that particular point in the region R. Okay, that's going to be important here because when we set our limits of integration, we'll be integrating in the z direction first. So we'll be going from lower z to upper z here. Now let's go ahead and consider the upper z first here. On the sphere, okay, we've got rho equals A. I went ahead and translated that into familiar Cartesian coordinates first. Remember, that's the square root of x squared plus y squared plus z squared. That's what rho would be. So that's set to A. Now x squared plus y squared, we all know, is r squared. So I have the square root of r squared plus z squared equals A. That would be a way of writing the sphere in cylindrical coordinates. Let's solve for z. Z is above the xy plane, so z is going to be the positive square root of a squared minus r squared. That, therefore, is going to be our upper z value. So that's our upper z right there. It's the square root of a squared minus r squared, whatever the r is, okay? All right, now on the cone, okay? On the cone here, let's come over here and pay attention to this. If I come up here, I'm interested in the z value corresponding to a particular radius here, okay? If you imagine the z value coming up here, after I take this point that's on the cone and project it onto the positive z-axis, I have that z value there. I could imagine what? A line that I've drawn in red emanating from that projected point onto the point on the cone, and that would make a right angle, right? Okay, because that's how we remember. That's how we define z coordinates, right? Okay, so that's a right triangle here. Now the angle right here is going to be alpha, right? So if you think about it, I've got a right triangle, and I'm interested in z in terms of r. Well, r would be the side opposite, and z would be the side adjacent. So I could write this equation: r divided by z is the tangent of that angle alpha. Okay? And then I could turn that around and solve for z. So z would be r cotangent of alpha. Alrighty? Alrighty, so this would be the lower value of z. Okay, so we'll be integrating in the z direction from this to this when we write our integral. Okay? Alrighty, so there's the picture. Let's come over here. We need to discuss the disk r. We said it's a circle centered at the origin of radius r naught. It's a specific radius here. See, I need to set my limits of integration for r here. Okay. So I'm going to go ahead and equate these two like this for that specific r naught. Now I'll square each side. This cotangent squared of alpha, so that's just some fixed number here. Let's solve for r naught squared. Adding r naught squared, we get 1 plus cotangent squared of alpha r squared. Taking square roots and stuff. Here, what's 1 plus cotangent squared? That's cosecant squared, isn't it? Okay, so we've got that times r naught squared. Taking square roots, everything's positive. R naught is a divided by cosecant of alpha, but the cosecant of alpha would be the sine of alpha. So this is r naught. So our integral is going to look like this for the actual volume. It's going to be the integral, okay, r dz dr d theta. Where's r going from and to? Well, it's z. What am I saying? Let's go from z, the lower z, so that's r cotangent alpha, to what? The square root of a squared minus r squared. Okay. Where's r going from and to? From 0 out to this, r naught, so that's a sine alpha. And then we're going all the way around on the circle, aren't we? So we're going from 0 to 2 pi. Now we want to be able to integrate this, so we'll work out that integral. Okay? All right, so let's go ahead and do that then. Okay. First part is going to be easy here. We're just going to be integrating, dz. There's no z involved here, so z is going to be going from r cotangent alpha up to the square root here. So then we'd be looking at, for the second integral, the z integral from 0 to a sine alpha. And then we've got our z's, alpha, or a squared minus r squared minus r cotangent alpha. And then we've got what? R dr. Okay, so we want to go ahead and integrate here the square root of a squared minus r squared, and I've got r dr, so I can make a quick change here. It looks like I'm going to get a squared minus r squared to what? The 1.5, so 3/2 power. And here it looks like minus 1/3 would do it for me, because of the derivative of a squared minus r squared would be minus 2r. Okay, so that looks good. Okay, right here I'd have minus 1/3 r cubed, right? Cotangent alpha, and then r is going from 0 to a sine alpha. Okay. Okay. So what would we get there? We would get 1/3 a squared minus a squared sine squared alpha to the 3/2. Okay, minus a negative, so that would be plus 1/3 when I let it be 0, so that'll be a squared to the 3/2. Okay, that takes care of that part. Here I would get what? Minus 1/3 a sine alpha cubed cotangent alpha. Okay, let's get through this. That's factor out the a squared. I've got 1 minus sine squared is cosine squared. So if I raise that to the 3/2 power, I would get a cubed cosine cubed alpha plus 1/3 a cubed minus 1/3 a cubed sine cubed cotangent alpha. Take out the 1/3 a cubed out of everything. And I've got what? Negative cosine cubed alpha plus 1 minus, that would really be what? That's a cube there, sorry. That would be sine squared cosine, wouldn't it? Because the cotangent is the cosine over the sine there. So that's what we would have there. We would have 1/3 a cubed. Let's go 1 minus cosine squared. And then I would have, no, just cosine alpha. Then I'd have cosine squared plus sine squared, wouldn't I? Alpha. Okay. I think that's right. Yeah, it looks good. So that's actually 1/3 a cubed, 1 minus the cosine of alpha, because sine squared and cosine squared is equal to 1. So this is almost the volume here. The last thing we need to do is get the volume, is integrate that quantity with respect to theta from 0 to 2 pi. And you see we get 2/3 pi a squared, or cubed, sorry, I keep writing squared, 1 minus cosine alpha. Okay, so there's our final answer. 2/3 pi a cubed 1 minus cosine alpha. Okay, by the way, if alpha is 0, then I get 1 minus 1, which is 0. I get a volume of 0. If alpha is pi, then I get 1 minus cosine of pi, so that's 1 minus negative 1, that's 2, times 2/3, that's 4/3 pi a cubed, which would be the volume of the entire sphere, right? Right? So if this was actually pi radians, I'd get the whole sphere, okay? And we know that is indeed the volume of the sphere. So it's just a double check at extreme values. Okay, well, that should keep you going then.